No problem. All right. Morning, everybody. Now let's see here. It's 11 on the dot, and we're missing a few people. So that's one reason why I typically give everybody a minute or two to read the questions on their own or talk to each other. Where are you going, Henry? What? Oh, okay. For a second, I thought you were leaving. Hi there, Mom. So let's see. I believe these are the same warm-up questions, but they bear repeating. Just in case. Like at this point, you should have the answers to these questions off the top of your head. That you could just be out on a first date or mingling at a social event, and you can just be talking about these things very casually. That's the hope, that we understand the techniques, but we also know conceptually what we're talking about. So read through, and we'll get started. Now, everybody who's here, does everyone have a copy of 3.3? I think we did, 3.3. And then did everyone get a copy of the practice test? Juan, did you get a copy of the practice test? You just did? Okay, good. Sarah's not here yet. Josh is here. I filled you in. Sarah, we don't know yet. Okay.
So the test is on up to 3.3?
Yeah, it's just sections 3.1, 3.2, 3.3. A nice little bite-sized test.
So it's Tuesday?
Yes, it's upcoming Tuesday.
I was like, what is that over there?
Yeah, I don't know what that is. That's the previous people that erased the board.
I was like, chapter 7 today. I was like, what?
That's just a mess, dude.
Yeah.
Yeah, chapter 7, 8, that's not even us. Okay, let's go ahead and read through these and get started. So, what does it mean to take an integral? Molly?
That's the area.
Yeah, we're just finding area under a curve. And it's the area trapped between the function and the x-axis. That's what we're looking for. And then how do you read the notation of an integral? So when I have this integral, and I go a to b f of x dx, what does every little part of the piece of that mean? So everybody can take one little part. Rosa, what one little part do you want to say?
The sum of a. Well, the s is the sum.
Yes, the long s represents a sum, and that is the sum of what?
A and b.
Right, the sum of what? What are we summing?
The 3?
Yeah, and specifically the area of what?
Rectangle.
Rectangles, exactly right. We're finding the sum of rectangles. How many rectangles? Infinitely many. How thin are those rectangles? Infinitely thin. How tall are those rectangles? F of x. Yeah, they're as tall as f of x. So there's summing, the long s is you're summing infinitely many, infinitely thin rectangles that have a height of f of x. Very good. Okay, so that's the long s. What does the a to the b mean? Or the a to b mean? Who wants to do that? No?
That's the interval.
Yeah, this interval we're doing. So like if you start from A, you're going to find this area, and then you end at B, and you get all the way up to this area. So A to B is just giving you kind of a boundary of where you're actually wanting to know where the area is. What's that, Henry? Oh, okay. All right. And then f of x is, yeah, it's just our function. That's the border that we're using to find our area. And so also f of x, as we already said, represents the height. And so what does dx represent? Yeah, the base, which happens to be infinitely thin, but hey, that's okay. Isn't that fun and interesting? See, in calculus, you get to talk about things that are infinitely thin and infinitely close, and it's meaningful. It really does mean something, People agree for hundreds of years. It's meaningful to talk about things that are infinitely thin and infinitely close together. Okay, how do you verbally describe how to take the derivative of a power function? So let's say that I had 5x to the third. Just verbally describe it for me. One, what would I do to take the derivative?
Multiply 3 times 5.
Yeah, multiply the 5 times the 3, and I'll even just leave the 5 there. And then?
Subtract 1.
Yeah, subtract 1, so we have that. So you'll notice that what we really fundamentally did was took the derivative of x cubed. X cubed became 3x squared, and the 5 was still just sitting there because coefficients come along for the ride. Okay, so multiply, subtract 1. So then how do you verbally describe how to take the antiderivative of a power function? So if I had 8x to the 7, how would I describe that one? Someone who hasn't said one yet. Colleen, go ahead. Yeah, you add 1 to the exponent.
And then you divide by the 8.
Yeah, and then you divide by whatever you get, which in this case you'd have 1x to the 8 or just x to the 8. That'd be wonderful. So that's how you take the power rule and the anti-power rule And then finally, the fundamental theorem of calculus, what does that state? So let's say that I actually wanted to take the integral, and in fact, let's make a very interesting question. Let's make up a fun, interesting question. Let's say that you had a upside down parabola that was only starting at 1. So we're literally curious how much area fits inside the bottom of a parabola. Like looking at it right side up for a second, I want to know how much area is just in the very bottom. So if I call this y equals negative x squared plus 1, then that's our parabola, and we're going to go from negative 1 to 1. So we're just curious how much area is there inside the bottom of the parabola. So we'll go from negative 1 to 1, and our function is negative x squared plus 1, and then that's dx. Okay, so now how do we actually find this area? And by the way, just for kicks, let's try to predict what the answer will be. If this is at 1, so I mean that's a 1 by 1 by 1 grid. Well, actually, that's a 1 by 1 square, and that's a 1 by 1 square. So the rectangle has an area of 2. So how much of that area do you think is being filled in?
2.
2 what? Yeah, the total rectangle is a width of 2 and a height of 1, so that total area of the rectangle is 2. This is more than half, right? So what do you think? 1 3/4? 1 3/4 maybe? 1 1/2 maybe? 1 1/3? You know, who knows? Okay, so how much area we're looking at? So then, what do we do first? Yes, the whole process is going to be called taking the integral. The first thing we'll do is take the antiderivative. So here, hold on. I'm going to go down once because I don't want to mess up my drawing. So I'm going to take the antiderivative of here. So I'm going to add 1 and divide by what I get. So notice I turn that negative into a negative 1 so that I can divide the 3 underneath. And then plus 1, what's the antiderivative of 1? 1x. And that's kind of something you kind of like to memorize, that anytime you take the integral of a single number, like the integral of 5, that's going to be 5x. And if you need to walk yourself through the steps, 5 is actually 5x to the 0. So if you add 1, that'd be x to the 1, and then divide by 1, you end up with the 5x that you expect. So the integral of a number is just that number times x. Okay, so there we have it. I did the antiderivative, so now I make my vertical line. I'm going from negative 1 to 1. Now what? Yeah, this is the fundamental theorem of calculus now, that you take what you have, and you're going to write parenthesis minus parenthesis. It's a structure minus a structure. And that structure is negative 1/3 something cubed plus something, and then negative 1/3 something cubed plus something. And what numbers do we plug in? Yeah, first I plug in 1, and you plug in the top number first. And then I plug in the bottom number, negative 1. There we go. And so now we can do some simplification here. So this is negative 1/3 times 1 cubed, that's just negative 1/3. And then plus 1, that's just plus 1. And then distribute, so minus a negative 1/3, but that's a negative 1 cubed. Look at all those negatives. So negative 1 cubed is negative 1. Negative 1 times negative 1/3 is positive 1/3. So minus 1/3 is minus 1/3. And then we have minus negative 1, which is plus 1. So does anything cancel? Nothing cancels. So I've got 1 plus 1 is 2, and then negative 1/3 is minus 2/3. And so our answer is 1 1/3. So the answer is 1 1/3. That's how much area there is in the bottom, the bitty bottom of a parabola. Okay, so there we have it. These are all the skills that we have. We're ready to keep going and finish section 3.3 today, and we'll even have some time to look at the practice test at that. So today's March 28th. Yep. When you come back on Tuesday, April 2nd, you'll all take a test. Okay. And I think I already told both of these jokes. I don't think I told the tissue joke. I did?
Yeah.
Oh, okay. They say no.
I remember
Well, I'll just tell it anyway. How do you make a tissue dance?
What is it?
boogie in it.
Yeah, you put a little boogie in it.
Put a boogie in it.
Oh.
Yeah, there you go. All right, so let's see here. How far did we get? We got all the way up to, oh yeah, we did some real nice problems last time. I think we finished. That's right, we started writing down formulas. Okay, great. And then we did a few, and we got all the way through number 4. Oh yeah, that's right, then we did both of those. Oh, we did that awesome problem right there. Did we finish it? Yeah. Yeah, we must have. We finished that one. And then we stopped. Okay, so here we are on number 8. So, anytime you approach an integral, probably the best first thing to do is to remind yourself, am I finding a definite integral or an indefinite integral? And that's a helpful distinction because then you can think about what your answer should look like. So if it's an indefinite integral, there's no upper limit and lower limit, and your answer is simply a formula plus c. Whereas if you have a definite integral, then you have upper and lower limit numbers, and then your answer is a single number which represents an area, right? So I mean, conceptually, that's a good way to start thinking about the problem. Should I be finding a formula right now, or should I be finding a single numerical answer? So in this case, what are we about to find? Formula. We're just going to find a formula. Yeah, plus c. So we want to go ahead and take our antiderivative. And as always, just like when we did derivatives, you have to kind of rewrite some of your terms so it's ready to be derived. So what do I have to do to 4 over x squared? Yeah, push it up into the numerator. So I have 4x to the negative 2 plus 3x. And just for fun, 3x, how am I going to write it? And to the 1, just to help myself out. And then plus 2, maybe now we have memorized now that the integral of 2 is 2x. You know, hopefully that's just become something that's muscle memory. But you could also rewrite that a little nicer so it's x to the 0, just, you know, to help remind you, oh yeah, that's going to be 2x. Okay, so we have it rewritten. We're ready to take our integral. So going down the line here, Sarah, antiderivative of 4x to the negative 2. What do you do? That would be the derivative.
No, you add 1.
Add 1, so that's the negative 1, and then?
And then divide by.
Divide by what you get. Okay, very good. And then antiderivative of 3x, Fatima? So what do you do first? Add 1, and then? Divide by what you get. Okay, very good. And then the last one, 2x to the 0. How about Colleen? Add 1.
And then you divide by.
Yeah, divide by what you get. Very nice. Okay, and at this point, I could go ahead and write plus c. So now we just clean up a little bit, right? That's just a negative 4, and then I push the x back down below. And that's just 3 halves, x squared. That's fine the way it is. You could write 1.5 if you wanted to. And then that's plus 2x, and then that's plus c. So just to reiterate this idea of plus c. See, right now, what we have is some function, which is the antiderivative of this one. And no matter what number I put there for c, if I now take the derivative of this, I will get back the original formula. And that's how you check that you did the integral correctly. You do the antiderivative, and then if you want to check your work, you take the derivative, and you check to make sure that you get back what you started with. So in this case, if I did take the derivative, the negative 4 over x would become the 4 over x squared, and the 3 halves x squared would become the 3x, and the 2x would become the 2, and the c would become nothing. And therefore, we do, in fact, get back the original problem. And that's why we put the plus c, because there's no one who could tell me that I can't put any number in the world right there. And when I check my derivative, I will get back the original problem. It's almost like a I'm not touching you version of math, right? Like, hey, I could put a number right there. It would be actually really funny and really clever if you were in a group of math people, like at a math party, and you finished your integral, and instead of writing plus c, you were like, plus 42. Because I can, right? Now, somebody asked the question, though, is there a right answer? And the way you'd find out if there's a right answer is somebody would actually have to tell you. So now, like, you took the integral. Let's say that this whole thing was f of x equals that integral. So now f of x equals this. So now at that point, the reason you have the plus c is somebody could say, I want this curve to go through the point, or the y-intercept. I want that curve to go through the y-intercept 5. So if somebody gives you an integral to do, and they say, hey, that resulting formula, I want it to go through the y-intercept of 5. Now see, now that nails down what the c value has to be. So if I want this function to go through 5, that means if I plug in 0, the whole thing should equal 5. So if I plug in 0, then, well, okay, I can't plug in 0, can I? Let me choose a different example. Forget the y-intercept. Let's say I want that function to go through the coordinate 1, 5. So I want that function to go through the coordinate 1, 5. If I plug in 1, the whole thing has to equal 5. Now suddenly this becomes a little more challenging, so I'd have to do, okay, f of 1 is -4/1 plus 3/2 1 squared plus 2 times 1 plus c, and I want that whole thing to equal 5. Now that's going to allow me to solve for a particular value of c, as opposed to just any old value of c. So what would that be? -4 plus 1.5 plus 2 is 3.5 plus c equals 5. So -4 plus 3.5 is -0.5 plus c equals 5. And so c equals 5.5. So that's how you go about solving for an actual c value. But it's only if someone came along and said, hey, you know that integral you just took? I really want it to go through that there point. If nobody says I want it to go through that there point, you just leave plus c, knowing that the c could be anything. The important thing about this function is that it has the slope characteristic that was determined by that equation. Because keep in mind, whatever this function is, if you take the derivative of it, so let's take the derivative of it, then the slope of this function is defined by the original function. Right? So this function, regardless of whether or not I shift it up or down by some number, has the same shape and therefore the same slope at every point along it, regardless of whether or not I shift it up or down. And again, that's why the c value doesn't matter, unless someone tells you. Okay, maybe I said too much. Is that okay? Who wants to ask a question about the plus c? Okay, well then let's keep going. All right. Take a look at that first one. Go ahead and give it a ponder. Write it down in your own handwriting. Think first, is it definite or indefinite? Think second, how am I going to take this integral? What formula applies? That's almost always a really good question to ask. What formula applies? And that's why we wrote down all those formulas on the first page. So take a look at it. Decide if it's definite or indefinite. What kind of formula applies? While you're doing that, I'm going to pull up a picture of this. We're going from x equals 1 to x equals 7. Okay, so everybody, take a look at this, the actual integral that we're doing here. So first of all, was it definite or indefinite? Definite. We're finding an actual area under that curve. Now look at how far we're going. We're taking this integral from 1 to e to the 7th. How big is e to the 7th? Yeah, 1,000, right? Just over 1,000. Now look at the graph. On your graph here, the highest, so that's 1. So we're going from 1 to 1,096, which is way over there. So even at 1, how tall is my graph? Yeah, like barely tall at all. That's 10. Wait, isn't that? Oh no, that's not 10. Well, that's 5 there. So yeah, 1, 2, 3. So almost 3. So we're looking at a graph that starts at 3, but then pretty quickly, because it's an asymptote, it's like infinitely thin and tall. Like it's barely tall at all, right? So how much area are we really going to get out of this thing? Yeah, not much. And more importantly, even if I just took the area here from 1 to 25, isn't that going to pretty much give us what the answer is? Because how much area is there really underneath an asymptote from 25 to 1,000? Minuscule, minuscule. So really, even if we just took the integral from 1 to 25, we're pretty much having the answer. That'll be close, right? Okay, so all that said, we understand what we're looking for, we understand what we're trying to solve. So we could even do both, just to see how much more area you really get by going all the way to 1,000 versus just going to 20. You want to see real quick? So let's say we do the integral. This will be funny. Huh. Okay, we're going from 1 to, instead of e to the 7th, I'm just going to go to 25. And we're doing 3 over x, dx. So that area is 9.65. Versus if I actually take my integral all the way out to e to the 7th. Oh, well my, that was surprising. Everything I said was completely wrong, wasn't it? Yeah, that's what happens when you make assumptions. You make an ass out of me. And that guy's not you at all, just me. So actually, how much area was there underneath that asymptote if you go all the way up to 1,000? Surprisingly, a lot. There I was thinking there wouldn't be very much area under that asymptote, but there was.
It's quite fun.
Yeah, and so I suppose that's because we went so far, like all the way up to 1,000, even though it's an asymptote, there's a lot of area there to be stacked up. Wow, that's very surprising.
Try 500 for the top limit.
What?
70 to 7, try 500.
Oh, just try something simple like 500? Yeah, that's only 18. As opposed to 21. Yeah, so between 500 all the way to 1,000, now is only a difference of, say, 2 or 3. Yeah. All right. Well, still, these are fun questions to ask because they give us a more conceptual understanding of what we're doing and how to make approximations. Okay, so what was the formula that we're going to use?
The natural one.
Correct, the natural log formula. It might be instinctive. As soon as you see 3 over x, we get so used to pushing variables up into the numerator that you might immediately, mistakenly, write 3x to the negative 1 and then try to do that integral. But as soon as you try, you add 1 and then divide by what you get, and it's undefined, and you're like, oh, I hit a dead end. So then you remind yourself, oh yeah, there's a special formula that's just 1 over x. I don't write it like that at all. In fact, what I write it like is this. That way you know that 3 is just a coefficient going along for the ride, and you're looking at the integral of 1 over x, which is a special formula on the first page of your packet, which is the integral is natural log. Now the 3, if you wanted to, just for fun, you could bring the 3 all the way out front. You could get that 3 completely out of there and say, that's 3 times the integral of 1 to the 7th of 1 over x dx. And then you're just kind of leaving the 3 out there, literally coming along for the ride as you do the actual integral on the inside. So then what? We do the antiderivative, which is natural log of x. We write in our vertical bar from 1 to e to the 7th. And we wrap that whole thing in brackets to remind ourselves that we're still multiplying it by 3. And then what? What do we do at this point? First, we rewrote it. Then, well, no, that's still rewriting it. There we did the antiderivative. And after the antiderivative, there was nothing to clean up. So we're just ready to do the fundamental theorem of calculus. So we do parenthesis minus parenthesis. Notice how many parentheses I have. That's a lot of structure. Because the 3 outside is still having to be multiplied by all that. So now we have the structure of natural log, the structure of natural log. And then into that, we plug in our various upper limit and lower limit, which would be 7 and 1. Now, we have not formally reviewed logarithms in this class. Both of those have very surprisingly simple answers. So let's just review a couple rules real quick. And we're only working with natural log in this class. I'm just going to write down the rules as natural log. But the rules would apply to LOG as well. So if I have natural log of AB, that's the same as natural log of A plus natural log of B. And if I have natural log of a quotient, A over B, then that's the same as what? Yeah, minus natural log of B. And then if I have natural log of A to the n, what is that the same as? Yeah, the n comes out front and becomes natural log of A. Which, look at that, doesn't that kind of remind you of the power rule or the rule of the derivative of e to the nx? The power comes out up front. Okay, so we can use this rule right now. And then finally, there's one other rule. What's the natural log of 1? That's 0. Now, you might want to remind yourself why that's true. I mean, on the one hand, you can just type it into your calculator, right? Natural log of 1 is 0. But let's say that you didn't know what natural log of 1 was. You're like, I don't know. What you do is you say, I don't know what it is. Call it x. And then you would say, well, this is natural log. That's really log base e of 1 equals x. And you say, well, this is a logarithm. Let me rewrite it in exponential form. So this is really e to the x equals 1. So you write e to the x equals 1. And then you say, well, what must x be for e to the something to be equal to 1? 0. Right? That's the only thing in the world that an exponential, that's the only number where an exponential equals 1. It has to be 0. So the natural log of 1 is equal to 0. That's a nice little process to remind yourself a lot of the intricacies and ins and outs of logarithms and how they work.
The all logs of 1?
Yeah. Yeah, if you take log base anything of 1 that equals 0. For the same reason, right? B to the 0 equals 1. Yeah. Okay, so what does that mean we can do here? Now we can call this 3 times, what's the natural log of e to the 7? The 7 comes out front, and then you're just left with natural log of e minus 0. Okay, what's natural log of e? You know, let's say that you forgot. Let's say you didn't know. Let's say you're having a pleasant dinner conversation with someone. You're like, oh man, I forgot my calculator. What's the natural log of e again? So what would you do? You'd say, I don't know what natural log of e is, so I'm just going to say it's equal to something. And then I rewrite it as log base e of e equals x. And then you rewrite it in exponential form, e to the x equals e. Which, I can put a 1 there to make it more visual. X is equal to 1. So now we have 3 times 7 times 1, which is 7, minus 0, which is 3 times 7, which is 21. And do you remember that was the answer from Desmos? It was 21. I think I still have it there. Yeah, there it is, 21. Alrighty. Wasn't that a nice problem? It was a really nice problem. It called upon a lot of prior knowledge about logarithms and how they work. Henry.
What if I had forgotten and then I just tried to do it and then I would run into a problem? Is you try to add 1 to the x to 0?
Right.
Okay.
Yeah, if you tried it that way, you run into it that way. Or let's say that you're like very confident and you're like, I'm going to rewrite this as 3x to the negative 1. Then I'm going to add 1, so x to the 0, divide by what I get, and you're like, hey, it's undefined. And then you just make the claim that this integral does not exist. Right? Now you can make that claim and you think that you've made a valid conclusion, but someone else would come along and say, well, actually, I mean, I looked at the graph. There really is a graph there, and there seems to be an area there, so it can't not exist. And then you have to go back and talk. But that's the wonderful thing about math, right? Is that any path you go, so long as you keep working, you'll get there. Like a dead end is not a bad thing. A dead end just tells you to turn around and go back, right? Unfortunately, psychologically, we all get bummed out by dead ends. We're like, oh, dead end, forget this, I'm gonna go get a snack. But a dead end is really just information, it's just data, it's a clue, and it's helping to point you back in the right direction. Okay, so how about the next one? Everybody go ahead and do that one on your own. I think everybody's seen enough examples now that you could do number 10. And in fact, 11 is pretty similar. So everybody, you can go ahead and work on 10 and 11. I'll just walk around and help. And then we're going to get to some problems that are
Nice structure in single parentheses. Yeah. Right here, this is the
Yeah.
and then here is that already. So once you've done the derivative, you can't do it already. Because that technically means do the derivative. They don't want to do it. So erase the derivative, erase the yes. And since you've already done the integral, now is the time to write it in vertical. That's as soon as you take that antiderivative, you use the vertical line. Because that's just a placeholder for the upper bound. And in fact, I suppose at that point you have the exact same numbers, don't you?
Yeah.
But what's the A?
Oh, that's just.
Oh, the A and B.
Yeah.
Oh, I see. Isn't it?
Yeah.
Oh, that's your reminder. Okay, very nice. Oh, I like that a lot. That's wonderful. Okay, very good. Yeah, nice structure. Sounds good. Keep doing it. Keep doing the antiderivative of both ones. Oh, so maybe I didn't get the answer 61.6. I got a much bigger answer. Yeah, well, we take a look at the graph. We're doing from 5x to the 5th to 6x to the 4th. We're going from -1 all the way to 4. But on the left-hand side, that's just a teeny amount of area. But look at the right-hand side. There's a lot of area. So I think it's going to be good. But your work here is correct. What are the exponents? It looks like your exponents are done. That would explain why your answer says. Okay, I want to do that. Okay, so what did you do? So what you did was you already did the antiderivative, right? So once you do the antiderivative, you don't let the long s again, or the dx, because that part is done. The long s and the dx mean do an integral. Now that you've done the antiderivative, put the long vertical line. That's probably why you got stuck. Now you're ready to do it from the here. Very good. Yeah. This was your original, and then this is the. Okay, very good. Now, just technically speaking, you want another vertical line so that every step along the way. I totally get why you didn't write it. You're like, you wrote it down and then you wanted to clean it up and then you wrote it. So that's what this is kind of like scratch work, huh? Yeah. Yeah. I mean, you could either put the vertical line in just to make it, technically correct, screw the whole thing out, and that way it's not even there. But you'd want the vertical line there or not? Oh no, I mean you'd want the vertical line there, just to be as technically precise as possible. But it looks good. Another one. So hey, I'm about to do this one on the board, so you can watch it right here.
Okay, let's review our answers real quick here. I'm going to do my integral right here. So we're going to take the integral from -1 to 4 of 5x to the 5th plus 6x to the 4th. And let's just remind ourselves, is this definite or indefinite? Definite. So we're looking for an area. Our answer should be one number. So first we do the antiderivative. So with the antiderivative, Juan, tell me the antiderivative of 5x to the 5th. What do you do first? Yeah, add 1, and then?
Divided by 6.
Yep, divide by what you get. Do the same thing here.
5.
Yeah, add 1, and then? 6 over 5, very good. Okay, so that's the antiderivative. Now folks, watch. As soon as you do the antiderivative, the ending and the beginning go away. The dx goes away, the integral sign goes away. So as soon as you do that antiderivative, there's no more dx, there's no more long s. Instead, you put in the vertical line with the -1 and the 4. So that's the first step, the antiderivative, and you get rid of the dx, you get rid of the integral symbol, and you just have your vertical line now. So now we do the fundamental theorem of calculus. And in the fundamental theorem of calculus, it's always going to be big parenthesis minus big parenthesis. And then, and this is just kind of like a lot of work you write down. You put in the parenthesis minus parenthesis, then you write in the empty structure. So this is 5, 6, something to the 6th, plus 6/5 something to the 6th, no, to the 5th. And then I have 5, 6, something to the 6th, plus 6/5 something to the 5th. So you write in a whole lot of structure, and then finally you put in your upper number and your lower number. Just want to make sure everybody has all that down.
So you do 2 sets of parentheses, like.
Always 2 sets of parentheses.
And then inside of parentheses, another 2 sets?
Well, it's like what you're doing in the fundamental theorem of calculus when you're actually going to take this and plug in those two numbers. First, you have the first parenthesis where you're plugging in the 4. And then you're going to subtract the second parenthesis where you're plugging in the -1. Now, what do you put inside each of those parentheses? The structure of the antiderivative. The structure of the antiderivative is 5/6 something to the 6 plus 6/5 something to the 5th. And that's what I wrote here. 5/6 something to the 6 plus 6/5 something to the 5th. And I rewrite that same exact structure again. So yeah, I mean, you can think of it in a lot of different ways, but you're essentially writing down the antiderivative formula twice with a minus sign in between. And then into that, you plug in your upper number and then your lower number. Now at that point, you know, talking about structure, you can just type that structure into your calculator once with the 4 in it, and then go back and edit it, that same structure, and put the -1 into it. I don't know that I would do this by hand. You certainly could. I mean, the numbers are not terrible. 4 to the 6th is already 4,096. So I'm thinking this would be quite a chore to do by hand. But instead, so watch when I do this, folks. When you type in the structure in your calculator, it should look like this. It should look like, I'll do it here. Parenthesis 5 divided by 6, parenthesis, parenthesis, 4, parenthesis, caret 6, and then plus, parenthesis, 6 divided by 5, parenthesis, parenthesis, 4, parenthesis, caret 5. So in case you didn't already type that into your calculator, go ahead and try it. Because I mean, the more you get used to typing things in like that, the more answers you're going to get correct. So 5 divided by 6, parenthesis, 4, parenthesis, the 6, then plus, parenthesis, 6 divided by 5, parenthesis, 4, parenthesis, the 5th. So now I know my first answer. And my first answer came out to be 4642.13 repeat. Now, I don't like writing down decimals. I'd rather write down the actual fraction. But it is a repeating decimal, so I suppose it's okay. Well, I'll just leave it like that. Because I can always math frac my answer at the end, right? You'll know what I mean by math frac. A special button on your calculator that lets you turn an answer back into a fraction. So now I do this one. So I hit second enter, and I go back and I change all those 4s into -1. So you have to hit second delete to insert the negative sign. So second delete, -1, and then second delete, -1. And that answer is -0.36 repeating. Now, hey, who has questions about their calculator? Who needs to know how to actually edit that? Or are you comfortable with just typing it on all over again? Because it's totally up to you. Now, you did -0.36. That's also repeated. So you want to put in a lot more 6s. Because now you're going to get the answer. Try that again. And in fact, you can time travel back to the second enter. It pulls it from the last thing you did. And so now you can just keep on. Came out wildly different than that. Your answer was what? 4642.49. And in fact, it rounded all the way up. Okay. Sure, did I do something right? 4642.13 minus 0.36. Actually, I didn't get the 0.5. Something went wrong with how I did it. You might want to start fresh. You can time travel all the way back to your original expression. There it is. What was that? Yeah, that's correct. So now if you enter, that'll give you the first question. And I would write it down as it is. So, okay, now watch. Then you go second enter, and you go back and change that 4. If you hit second insert, type in -1, then you get rid of that extra 4 there. Then you go back over to the other 4. And second insert, you see that one as well. Then -1. Now you have 2 decimals there after. So that one, write those down with your repeating ones. That's what you did. Then just try typing that in. Because you can totally type in 4.3.1. Just do enough for each to fill one. And then -1.36. Now you can see it. Okay, did it all work? Did it work?
At first, no. I just changed it.
Oh, I see. Wait. Oh, right. Well, and the reason it didn't work is because your 6 is inside on the -1, it's placed on the outside. Because your calculator actually thinks that this is 1 to the 6th, but make it negative. And that's very different from doing negative 1 to the 6th. So we can time travel back. Okay. Where you did that. And you would need to flip. That's where this is. Right? There. There. Now that's actually negative 1 to the 6th. Try that in this one. You know the insert button? Yeah. How do we go? Hey, how strange, you got that too. One of us also got that.
Mr. G.
Oh, so it should be plus. Folks, it's minus a negative. Yeah, so Colleen, that's why our answers were not correct. It's minus of minus, so that's actually be adding those two numbers together. Time travel back to that part of your calculator, change the minus to a plus. Yes, Josh?
I got, instead of 0.36, I got 2.0.
Listen. Did anyone, let's just start comparing answers real quick. Did everybody get, what was the answer there, Juan? 4642.5? Yeah, I believe that's it. And in fact, don't I have the answer on the screen? Yeah, there it is. Yeah, so there's the answer. Okay. Josh? Oh yeah, so same thing as what he did. You need the exponent on the outside of it. Yeah, there you go. Now you'll get the answer. Okay, and were you able to time travel back and change that?
Oh, no.
So if you hit second enter to there, where we're subtracting those two things, or did you change that to plus? And now we can try that all again. Try all those computations again and make sure you get it all correct. Okay, what was it? No, okay, well, you're going to use mine right now. You lost it. All right. Let's see here. So did it work?
Yeah.
Oh, so everything's fine.
Yeah.
Oh, okay, great. And it all worked out on your calculator too? Yeah, that's worked. That looks good. Sarah, how about you? Everything worked out okay on your calculator? Okay. Okay, wonderful. Everybody, I think we're all on the same page here. I think all of our calculators worked. Everybody got the answer? Did you find the problem with those exponents that worked out? Yeah. Well, now you know. You're going to pay a little more attention to it. All right. Well, there we have it. Folks, in case you didn't already, you might already be working on the next problem. But come back for a moment and look at the original problem. So the integral by Desmos was 4642.5. And if you just look at the graph, what is our graph? We're going from -1 to 4. So how much area is there between -1 and 4? I mean, over here, not much. But look what's happening over here. A gigantic amount of area, because that line shoots up. And so just imagine how tall that thing goes by the time it gets all the way over here to 4. So that's a lot of area, and 4,000 is a reasonable answer. Okay, I tell you what, for the sake of time, let's not do the next problem, because it's very similar. Or do you want to go ahead and do it because it's so similar? I mean, that's good practice to do something almost the same right in a row, because it solidifies your understanding. Go ahead, everybody, finish that second one. And I'll put the answer up on the screen so you can check. Oh, it's really good. Great structure in parentheses. Yeah, one more time. Anyway. Oh, I didn't know that. Was it on the calculator that you did that? I think they calculated it. Did you like that? Oh, you did, yes, 6 11. Okay, so you know that. We can plug in the 1 point, top of the box.
Just like we read above.
Top of the box, yeah, and it changes.
Yep, exactly right. There you go. Very good.
Nice one. Yeah, that structure was very good.
Nice. Work out.
Yeah, looking good.
Very nice one. That looks great. Okay, a lot of you are wrapping up the problem. You can take a look at the solution on the board, especially look at the actual area that we're looking at. So we're looking at the function 4x to the 4th plus 6x squared. That's this nice parabola looking thing. We're going from -2. Yeah, you're going from -2 over to 1. So I've got my vertical lines there. So you can see that this is the amount of area and that's the amount of area. So the area turns out to be 44.4. Any thoughts or questions? Was that helpful to do 2 in a row that were almost the same? I find it very helpful to do multiple problems in a row. All right. Okay, this next question. If we were doing a derivative right now, what rule might come to mind? Well, the zero product rule, that would allow us to solve that for x. I mean, just look at how many things come to mind as you look at this problem. If somebody merely gave you the function x plus 4x minus 2, you would say, hey, those are x-intercepts. Because by the zero product rule, if you want to know where the x-intercepts, you set both of those equal to 0, and you would have a graph where one x-intercept is at -4, the other x-intercept is at 2, and it's a parabola, so it looks like this. Okay, so then between the parabola and the x-axis. You'll notice what this problem doesn't do is tell us where to actually find the area. They merely want the antiderivative. So by asking for the antiderivative, they're saying, find a function whose slope is this, right? Because consider this in symbolic form. Whenever you take the integral, you're really taking the integral of f prime of x in order to get f of x. Let your eyes rest on that for a little bit to make sure that that makes sense to you. Because normally when we take the derivative of f of x, that's when we get f prime of x. Whereas if we take the integral, we'd be taking the integral of f prime of x in order to get f of x. All right, so you see how the order changes? So that's what they're really saying, is they're saying, you know how x plus 4x minus 2 would represent a parabola? And you'd normally think of the parabola as the function you're interested in. But they're saying, no, no, do not think this is the function. Consider this to be the derivative this is the derivative, and go back and find me the original function. So if that was the case, recall what can we say for sure? If you're looking at the derivative formula, okay, so this is the derivative. Every point on here represents a slope of the previous graph. What did the x-intercepts represent again? What do the x-intercepts of the derivative? They represent flat spots. So now I know on my original graph, I should have a flat spot at 2, I don't know where, and I should have a flat spot at -4, I don't know where. And by I don't know where, I mean the flat spot could be anywhere vertically. Flat spot could be anywhere vertically, and it could either look like a flat spot up here and then a flat spot down there, or it could look like a flat spot down here and then a flat spot up there, right? So do we know what our flat spots look like on this graph? What could we figure it out? What's the derivative? What's the slope in between the two? Yeah, the y values of this derivative function are negative. So that means that in between the two flat spots, there needs to be a negative slope. So now I know that my graph should look like this, because in between the two flat spots, the slope should be negative, because the y values of my derivative are negative. So now we can really kind of piece something together. We can say, hey, let's say my flat spot is there, my other flat spot has to be below it, because that way it's going to go down and do something like that. Okay, so there, we just kind of pieced together what the answer to this thing is going to be. It's going to be some sort of cubic. And that's about all we know. Okay, so now how do we go about doing the problem? Yeah, FOIL is the right answer, because you might recall that if we were simply taking this function and trying to do the derivative, then we have a special rule, and that's the product rule. If you wanted to take the derivative of this, you could do the product rule. You could say the derivative of the first, so plus 2. So you can say the derivative of the first times the second plus derivative of the second times the first. So if you were doing the derivative of a product, you could use the product rule. But we're about to do the integral of a product. Do we have an integral product rule? I've certainly never told you about one. Was there word on the street? Like, so can we do the integral of a product? We don't know how. We don't know how. That's not to say it can't be done. We'll do it after the next test. But we don't know how to do the integral of a product yet. So that means we have to make it not a product. And Josh, how do you make it not a product? FOIL it out. Right. Okay. Okay, so now we're ready to do the problem. So we're going to FOIL that out. So we're actually doing the integral of what? First, and now take your time. If you can FOIL in your head and get the right answer, this is going to be x squared plus 2x minus 8. Great. You can FOIL it out in your head and get the right answer. But if you need to just show some work somewhere else, do some scratch work, by all means. You know, come over here to somewhere else and jot down x plus 4, x minus 2, do the full FOIL process first, outer, inner, last, combine like terms, x squared plus 2x minus 8. I really recommend that you do that kind of scratch work somewhere else, because that keeps our integral clean and tidy, just going from step to step to step without scratch work bogging it all up. Okay, so do the antiderivative. Once you do the, where's your other? You have 3 terms there. The derivative of 8 is nothing. The antiderivative of 8 is something. There you go. Very nice. Oh, good. You scratched that out. Okay, very, very nice. Yeah. To be 1/3 x cubed plus 1x squared minus 8x. That's what you got? Yep. Yeah, very nice one. First one. I might recommend writing down the variable one first. And in fact, put a little 1 up there. By making the 1 even more concrete, then you can more clearly add 1 and then divide by what you get. Very good. Okay, you all can check your work. Add 1, divide by what you get. Add, oh, put the 1 there. Add 1, divide by what you get. And put my x to 0 there. Add 1, divide by what I get. Now, folks, do you see how formal I did that by leaving each one as a fraction, even though 2/2 is ridiculous and 8/1 is ridiculous? And I put in the x to 0, even though I just have memorized the antiderivative of 8 is 8x. I did it that way because If that's just how you treat every anti-power rule, you just get yourself in a routine and you become a robot. And as a robot, you become very efficient. You just always follow the same steps every time, and bam, you just apply it. So then, like I said, so I robotically did the antiderivative, and now I go back and I clean it up and I say, well, that's 1/3 x cubed plus x squared minus 8x plus c. Okay.
That's the answer?
That's the answer. And of course, let's check that. What were we expecting in our antiderivative graph? We were expecting, we wanted, so I'm sorry, 1/3 x cubed, was it plus x squared?
Yes.
Minus 8x? Okay, so there's our graph. And did we in fact have a flat spot at -4?
Yes.
Flat spot at 2?
Yes.
Decreasing slope in between the two flat spots? So it had all the properties we wanted. Now, could I shift that thing up? And up, and up, and up, and up, and up, and up, and up? And does it still have all the same slope structure?
Yes.
Still has the same flat spots at the same location, still decreasing in between. I can take that same thing and I could shift it down, and down, and down, and down, and down. And by shifting it vertically, it still has all the same slope structure. Has the same flat spots in the same location, same decreasing slope. The entire shape of that curve is identical. It's merely shifted downward or upward. All right. Any questions? Oh, my phone went off. Let's take a break. I was just going to plow right on through there. 11:57. Let's be back at 12:07. Great. I think we're almost good. 12. Let me just see. So, wait, for this one. Oh, this one. I'm sorry, 11. Yeah, what was the answer? 44. Okay. So let's.
I got this one.
Yeah, this one. Let's type that in differently. Just type it in again. Now, can I show you how to type it in? Okay. So when you're going to type in something like this, first of all, the 4/5 has to be parentheses. Or the fraction's always going to be parentheses. And then for parentheses, -2. And then to the power 4. Wait, that's just now plus. And then you do the whole thing over again. So you're going to have parentheses. 6 divided by 20. And then that goes right into another parentheses, -2. And then raise it up. Now notice those parentheses, those are all the parentheses that we write down in the structures we write down. Like those parentheses are part of the structure you write down. And you filled in the -2. So I think the only thing you'll have to additionally add is the parentheses around the oh, that's what you got. I don't think you do. Yeah. We're actually the 6
Oh, no, I don't know why.
I'm getting my hopes up.
There we go. That'll change the whole thing, Jose. You're welcome.
I mean, I want to do
I know you'd have to find a diagram of all the wires and then you have to split them into.
I can barely do this. I'm not gonna do this kind of. I mean, if it's like color coded, like, I might, but I'm gonna have it going to this.
No, I just kind of learned it myself.
There's one more practice test up here in case anybody wants it. Ready?
there's one more minute, but we can skip it. What's that? All right, so folks, in the last problem, we said that it looked like a product rule, right? It looked like a product rule, but then we agreed that we don't know a product rule for integrals, right? So we didn't know a product rule for integrals, so we FOILed it, and then it was no longer a product, right? So look at this next problem. It looks like what derivative rule? The quotient rule. But again, we don't have a quotient rule for integrals. So if to get rid of a product, we FOILed it, and then there wasn't a product rule anymore. Here we have a quotient. How do we get rid of a quotient so that we don't have a quotient anymore? We could divide. Now what does that mean? How do I divide that?
Split up.
Yeah, we'll split up the numerator into two separate bits. Let's see if that helps us.
So we're going to keep the integral symbol because we're just going to start rewriting. So now I have 6x squared over root x plus 8 over root x. And you'll notice that now all of a sudden, conceptually and mentally, we're no longer looking at a quotient rule. We're just looking at two polynomial terms where we have to push all the variables into the numerator, right? So the problem really quickly took care of itself by just splitting that fraction. So now again, though, that root x, now you might be feeling a little tired of rewriting the integral every single time. Like, gee whiz, why am I rewriting this integral every single time? That seems like a lot of work to rewrite this integral every single time. And that's fair. You know, maybe what you want to do instead is just do some scratch work. So you take your 6x squared plus 8 over root x and break it up over somewhere else on the side. Just doing your scratch work somewhere else. And then, what happens then? How do we push this x to the 1/2 into the numerator? Right. So there's two different exponent rules you can remember. One is that x squared over x to the 1/2, the rule is you subtract. So that'd be x to the 2 minus 1/2. Right? So that's really x to the 3/2. Or, sure, you could just turn that into a negative 1/2. So you'd have x squared times x to the negative 1/2. And then the exponent rule is to add. So that'd be x to the 2 plus negative 1/2. Either way, you end up getting x to the 3/2, right? You just have to remember that exponent rule from long, long ago. So now we have 6x to the 3/2. And then this x to the 1/2 pushes up neatly into the numerator without needing to do anything to it. It's just x to the negative 1/2. Okay, so whether you do all that work somewhere else, or you do and just keep rewriting the integral, now we're really ready to do our integral. So that's 6x to the 3/2 plus 8x to the negative 1/2. And psychologically, I'd like you to appreciate. Let your eye fall on this integral, and then let your eye fall on this integral. And look at the difference between the two. Isn't it an amazing difference? This one looks really, really hard. This one, you're like, oh, okay, I've already done ones like that. And if that's not a metaphor for life, I don't know what is. You know, you're confronted with a hard problem, you think it's really hard, and you go take a nap and have a snack. But really, if you reconceptualize the problem in a different way, you realize the problem is really quite simple. You can move on with your life. Okay, so now we do the antiderivative. So add 1. How do I add 1 to 3/2? Instead of plus 1, I'll do plus 2/2. So plus 2/2. So that gives me x to the 5/2. And then divide by what you get. So 6 divided. Now, whether you can just do 6 divided by 5/2 in your head, and you're like, oh yeah, that's 12/5. Or you want to go do some scratch work somewhere else, I would just write it down. You know? So I added 1 and divided by what I got. And then over here, I'm going to add 1. So what's negative 1/2 plus 1? Again, negative 1/2 plus 2/2. So that's 1/2. So x to the 1/2, and then divide by what you get. 8 divided by 1/2. And again, maybe you feel comfortable just doing 8 divided by 1/2 in your head. But I would just write it down. And you know, I like to play it safe. Okay, so now, whether you do scratch work or do it in your head, I'm going to go do some scratch work. 6 divided by 5/2, which is really 6 over 1 divided by 5/2. It's really 6 over 1 times 2/5, which is really 12/5. So there's my first answer, 12/5 x to the 1/2, or 12/5 x to the 5/2. And then 8 divided by 1/2, again, just to make sure, 8 divided by 1/2 is really 8/1 divided by half, is really 8/1 times 2/1, which is really 16. So now I have 16 next to the 1. Now, folks, in all of my enthusiasm to do this fraction work, what have I completely forgotten about? My vertical line with my placeholders for the fact that I'm integrating from 3 to 5. Integrating from 3 to 5.
Oh, yeah.
Yeah, and that's what was missing. I got carried away by the excitement of doing fractions. All right, so now we have our antiderivative. It took one step to clean it up. And now we're prepared to do our fundamental theorem of calculus. So just imagine and look at how exciting this is going to be. And then really what we're about to do is calculator skill. Right, because we're going to have to do big fraction minus, big parenthesis minus big parenthesis. And we need to type in all that structure into our calculator. So, for instance, I'm going to type it in up here just the way you would on your calculator. It'd be parenthesis 12 divided by 5, parenthesis, something to the caret, parenthesis 5 halves. I ran out of room. That's a lot to write down. I'll probably just have room to write that part. Plus 16 parenthesis, caret, parenthesis to the 1/2. So there, that's just the structure of the first part, which is all you're going to type into your calculator, right? You're going to type in that once, put in the top number 5, and then hit second enter, call up the structure, and change the 5 into a 3. But I will go ahead and write it down again. So again, that's parenthesis 12 divided by 5, parenthesis something to the caret, parenthesis 5 halves, plus 16, parenthesis, caret, parenthesis 1 divided by 2, parenthesis. And so the first one, I plug in 5, and then the second one, I plug in 3. Wouldn't it be interesting if we all wrote math on our paper the way we type it into our TI? Yeah, it feels like it would, right? It would take a more horizontal space to be sure. Especially the fact that you put in the caret symbol instead of just writing a small and a pi. Well, I like how you're doing that. You're drawing your little line to show what the decimal value is right below it. That's nice. Very nice. Did I give my calculator to someone? I gave it to you, right, Rosa?
Yeah.
Okay. Now, I have to admit that I'm probably going to put a problem like this on the test. Because it's such a good problem. So let's see what that looks like. That's numerator 6. Numerator 6x squared 8 divided by denominator of x. As far as graphs go, that's probably one of the least exciting graphs ever. I mean, what does it look like? Looks like a slightly deformed parabola. Not very exciting. Oh, I take it back. That's not at all lopsided parabola. Really, what is that? You have an asymptote going up the y-axis, and then this way, well, it's not an asymptote. It just keeps going and going. So that's what our graph looks like. And what are we finding the area between? Between 3 and 5. So here's my vertical line 3. Here's my vertical line 5.
And that's how much area we're looking at. Really, it looks like a trapezoid, doesn't it? It's a fairly good trapezoid, in fact, because that red line is not very curvy. So if I wanted to right now, geometrically, I can go ahead and solve. I can go ahead and solve this trapezoid, 1/2 b1 plus b2 times the height. So you have to turn your head sideways. My height is 2. And then that 1/2 and the 2 cancel out. So then I'm really just adding the bases. So that first base has a height of 34 roughly. And the second base has a height of 71 maybe. So then the 1/2 and the 2 cancel out and I get 105. Did anyone get anything close to 105? 104.8, folks. I mean, my goodness, that's awfully close. So then I can go ahead and actually ask Desmos to do that for me. And since I already put the function in to graph it, I can now just call up my functions and put a little integral symbol right in front of it. I don't have to retype anything. I just go from 3 to 5. And it won't work until you type dx. And yeah, 104.8. Wasn't the trapezoid method remarkably accurate? That's really surprising. I didn't have a calculator, so who can tell me what those 2 decimals were, just so everybody can check their answer?
1.816.
What?
104.816.
104.816, 0.5. Sorry, minus.
Oh,
169.9. Okay, I need all that again. What's the first one?
169.94.
Okay.
And then 65.93.
Okay. There, so that's what your actual decimals would have worked out to, if you had typed those both in separately. Is that what anybody got? Maybe. Now, if you're looking at your paper, and those are the numbers you see, then that's a really exciting opportunity for you to go back and find your numerical mistake. Right? Now wait, does everyone agree that that's correct? Yeah? Okay. I mean, it certainly does give us the answer, 104. I'll share with you a personal anecdote. Yesterday I was working on my homework, because I have homework, I'm in math class. And I swear I spent 1 hour working on a problem. It was a full sheet of work. I could not find my mistake. I reread the textbook. I posted a question on my online forum. Nobody even answered my question. Kept looking, and finally I found my mistake. Embedded within all my work, there was a 1 that should have been a 1/2. It took me a long time to find that mistake. And boy, did I kick myself afterwards. I mean, just something so little as a 1 that should have been a 1/2. Oh! But you know, experiences like those train you to go a little slower, be a little more careful, and then it also trains you to be a Sherlock Holmes, and you have to go back and find a mistake, and where did I go wrong? And that skill right there is a skill that employers want. Right? Employers want the skill to be able to go back, go through lots of data, and find a mistake. Wasn't?
So the period problem on the when we period the
On the previous problem?
like
On this one? Oh no, the product one.
Yeah. Unit or
Yeah.
We didn't put the parentheses on the
Exponent?
exponent, right?
We did not, because the exponent was just a single number.
Okay, so when
Whereas now the exponents are fractions.
so when the fraction like exponent you have
If it's a fraction, it always goes in parentheses. No matter what, if you're typing in a fraction, put it in parentheses.
okay.
All right, well, very nice, folks. Well, like I said, I think I'll put a question like that on the test, and it's certainly on the practice test. Any questions on that before we move on? What's wrong? Oh, goody. Yeah, that's the answer. Oh, like how many decimals do you keep? Well, that's a really good question, folks. What do you think? How many decimals should we keep? Does anyone have that answer in their calculator? It's 104.816. That's how it starts. And I'm just curious, if we math fract it, it doesn't even turn it into a fraction. So apparently the fraction is so complicated that the calculator doesn't even want to turn it into a fraction. So, you know, it always, as a rule, more, the software system where you're doing your homework, wants 4 decimals of accuracy. So in that case, it'd be 104.8161. Because that 0 would round up from the 5 after. So I would say 4 decimals of accuracy amongst friends. Maybe a nice t-shirt, 4 decimals of accuracy amongst friends. Yeah. Okay. Well, folks, we just have 2 more word problems to do, and then we can take a look at your...
Why are you in math?
Because I'm working on my master's in that. In order to even work for any community college in Arizona, you have to have a master's degree in the field of teaching. So I was previously a high school teacher, and I had a bachelor's in math and a master's in education. But to become a gateway to teach, you need a master's in the field of teaching, you need a master's in math. The minimum requirement is half of the degree. So I hurried up, got half the degree, applied, got the job. And now I'm just finishing the rest of the degree. I'm just finishing because I want to. You know, gateway is not requiring me to, I have the minimum credits. But I mean, that's almost like anything for any career that you all want. You might just need to get some sort of credits to have the prerequisites that now you can get hired. So I'm just finishing to see if I can hack it. I've always thought of myself as a mathematician, but until I get a master's and a PhD, I don't know, maybe I'm fooling myself. Yeah, so I'm doing it personally to see if I can hack it. All right, what's that? Yeah, I can. You see these movies like Good Will Hunting, you know, Good Will Hunting, all these math geniuses, and you're like, oh, they're geniuses, or they're just people like us. Have you tried that? Okay, I'll go home today, I'll do it. No. Okay. What's that, Josh? Yeah, no, I don't know anything about that. All right, so we've got a little word problem up there. Now, what do most people do when they see a word problem? Go to sleep. Take a nap, have a snack. So let's just look at it and think about it. Yeah, go for a walk. It says the traffic flow rate of cars per hour across an intersection is given by that equation. So what is flow rate anyway? What does that mean? It's the flow rate of cars per hour. Yeah, it could be the average or just how many cars are going through the intersection. So can you all imagine an intersection somewhere in your neighborhood or by your house or just any intersection with a high flow rate? Just constantly cars, always there, tons and tons of cars going through that intersection. So that'd be a high flow rate. Whereas you can all imagine an intersection in the middle of the country, where like maybe 1 car per hour actually goes through. It's like this country bumpkin road. And there's no cars at all. So now let's see what this flow rate actually says. It's R of t equals this polynomial. Now, why did they write it backwards? I don't know. That's pretty strange, isn't it? Okay, so we have this flow rate where t is in hours, so that's hours. But really, they're saying t is in hours and t equals 0 is 6 a.m. So really, t represents the time. Because let's think about that for a second. If I make my graph, and they're saying that t equals 0 is 6 a.m., then what's t equals 1? Yeah, that's 7 a.m. And then what's t equals 2? 8 a.m. So really, I mean, this might feel kind of strange. They're defining our input variable starting at 0, but 0 means 6 a.m. in the morning. And probably because, you know, that's when people are waking up, that's when traffic really starts. Is there a lot of work traffic? Work traffic at 3 a.m.? Not a lot of people going to work at 3 a.m. There's traffic, but it's not people going to work. So I guess they just figure 6 a.m. is the beginning of when people start going to work. Okay, so we have our numbers here. 3 represents 9 a.m. And our flow rate then is R of t up here. And what's the unit there? It's just cars, right? Yeah, so it's just total cars. It's not tens of cars, it's not hundreds of cars, it's just cars. So just for fun, you know, whenever you start a word problem, it's nice to just spend some time getting to know the problem. Like for instance, I just made a little graph. That helps me. You know, I know a little more now about what the graph represents. This axis is my time, and this axis is the number of cars. And furthermore, it helped to just plot a couple points. You know, why not? So what's the flow rate at t equals 0? Yeah, those two terms go away, and it's just 500. So at 6 a.m., the flow rate is 500. Now, what does my graph look like? What kind of a graph is it? It's an upside-down parabola. So let's keep that in mind. It's probably going to go like this. Well, let's go ahead and plug in the next one. If I plug in 1, that's 500 plus 600, which is 1,100, minus 150, so that's 950. So already, by that, we're at 900.
That makes sense.
Yeah, then it's going up over time, right? Because people are waking up, more people are getting on the road. And theoretically, the traffic will go up, 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 up. But at some point, the traffic is going to start to die down because everybody's going home and nobody's still driving, going to or from home. So now, how long does that arc go up? I have no idea, and I don't really care to input 2. We could do it. 500 plus 1,200 is 1,700. 2 squared is 4. 4 comes out to 600. So that'd be 500 plus minus 600. Is that 1,100? Now, there's no need to try to do this in my head. That's kind of silly. But so far we can see that we've got something going on like that.
And of course, probably the best thing that we can do is just use this graph. So let's see what our graph looks like. And we have to fix our units. Now, see, now that we've done a couple points, I know a lot more about what units I'm going to use. I'm just going to go left 1, and at most, I'm going to go right 12, 6 a.m. to 6 p.m. So maybe I'll put in 14 just for kicks. Oh, there's the graph. It's already coming back down. And then my vertical axis, I know, is already up at 110, so I'll just put 200. Oh, 200 is not high enough. I'm going to go 500, still not high enough. 700, still not high enough. 900. My goodness, that's a lot of carbs. 1200? All right, there we go. So now what are we looking at here? I don't understand this model because apparently by t equals 4 or t equals 5, the traffic has already died back down to 0. I don't know if that makes any sense. Did I type it in correctly? 500 plus 600x minus 150x squared.
Weird town.
Yeah, very weird town, right? Part of me wonders if we did this wrong. Oh, but look at the model. If you read now, it says how many cars pass through the intersection between 6 a.m. and 8 a.m. So they're really only interested in very close, 6 a.m. to 8 a.m. That's only 0 to 2.
Oh,
So maybe this is only a model of morning traffic.
that makes sense.
And maybe it doesn't at all. It's not supposed to model people during the day, because during the day people are at work. So maybe this is just modeling the morning rush. Okay? So we've learned a lot, haven't we? Like, just by playing around with this function, looking at it, we have a really good understanding of what we're looking at. And all they're asking for is the number of cars going through between 6 and 8 a.m., which is really between 0, so x equals 0, and x equals 2. So that's all we're interested in is that area right here, which roughly speaking is a trapezoid. We can find the area that way, but let's just go ahead and do the integral. So after all that, what are we going to do? We're just going to take the integral from 6 a.m. to 8 a.m. So I put from 6 to 8. Well, which is it, 0 to 2 or 6 to 8? 0 to 2. 0 to 2. Because t is our variable, and 6 and 8 is just what it represents. So we're going from 0 to 2 of this function, 500 plus 600t minus 150 squared. dt. So you notice now we have a dt because the variable for this formula is t, so they're using dt. So ultimately, just take a look at what we're about to integrate. This is probably one of the easier problems that we've had.
Does it matter when you put 2 in 0?
Or what do you think? Let's think about what the integral from a to b represented again on a graph. On a graph, we're saying that a and b is the beginning and the end. So for sure, we're going from 0 to 2. So it seems that 0 has to go on the bottom and 2 has to go on the top. You could think of it as going from left to right, and it always goes from left to right. That's one way to think about it. But Rosa, go one step further. You're about to take the antiderivative. So if that's f prime, this would be f minus f, the fundamental theorem of calculus. If you do switch the b and the a, like let's say you do it this way, the proper way, versus what if you did f of a minus f of b the wrong way? What would happen to your answer if you switch those? Consider a simple example. Let's say that you're about to do 10 minus 8, but instead you did 8 minus 10. What will the difference be between your two answers? Yeah, one would be 2 and one would be negative 2. So does it matter if you switch to A and B? Yes. But only to the extent that it changes the sign. It's not catastrophic, it's just the opposite sign. And then you look at it and say, the flow rate is negative 500 cars? And then you'd be like, oh, it can't be negative 500 cars. Yeah. Very good question, Rosa. Did that answer your question? Okay, so is everybody just about done with the integral? So that gave us, I'm going to put in my t to the 0 and t to the 1. So add 1, divide by what you get. Add 1, divide by what you get. And add 1, divide by what you get from 0 to 2. So that's just 500t plus 300 t squared minus 50 t cubed from 0 to 2. Now, on a personal level, what's so exciting about having one of your integration numbers 0? You don't have to do it, right? Because the fundamental theorem of calculus would say parenthesis minus parenthesis, and here I'm going to plug in 2, and here I'm going to plug in 0. Variable in each term, that whole thing is a 0, so we don't even have to do it. So really, we're just plugging a 2 into all of that, which you could darn near do in your head without using your calculator. So 500 times 2 is 1,000. And then 2 squared is 4 times 300 is 1,200. And then 2 cubed is 8 times 50 is minus 400. And so that would be, what, 2,200 minus 4? Did anyone get 1,800 cars? So keep in mind that's 1,800 cars total. I said, how many cars pass through the intersection between 6 and 8 a.m.? So this is not a flow rate. This is not a flow rate. The function was a flow rate because that was cars per hour, which interestingly enough, that formula, you could plug in 6:30 a.m. You can plug in 6:45 a.m., right? Like if I plug in the number 0.5, that would be the flow of cars through the intersection at 6:30. I can plug in 0.83, and that would be the flow of cars through the intersection at 6:50. I can plug in, any value of t, and it's telling you the flow rate at that exact minute. Whereas now what we just calculated was just the total number of cars that went through that road. Did we say everything there is possible to say about this problem? Well, maybe so. Folks, sometimes I feel a little torn. Like in here, I really want to make sure we understand everything that we're doing. And at the same time, I realized I could have just, how long did I spend on that problem? At least 10 minutes. I could have just gone up here and said, write down the integral, solve the integral. But I think exploring a word problem, really understand what they're talking about. Even the fact that we figured out that this model is only for morning traffic, that's kind of exciting. We figured something out. And discussion, the difference between flow rate of cars per hour versus total number of cars. That's all interesting. That's really your job as a student or an employee or owning your own business to really understand and get down into the nitty-gritty of what you're talking about. All right, one more question. So, a company's marginal cost function, what company is it? Any company. Which company? Anybody want to say what company it is? Nike? All right. So Nike's marginal cost function is that. So I'm going to write down the marginal cost function. 11 over root x. Wait, did they recently lose a lot of money? Oh. I don't even know who you're talking about right now. Stormy Daniels. Scandalous person. Do you think that's how each introduces themselves? Like, well, okay, so we have this marginal cost function. What does that mean again? That is a marginal cost function? Well, that's true. It's the slope of the original cost function. But marginal cost means it's telling you the cost of the very next item. So if I write down C prime of 57, what did I just calculate?
The cost.
Right. Cost of 57. Yeah, okay, so just so we all remember what we're doing. So then, for instance, what would this be? You say undefined because you plugged in the 0 and you divided by 0, that's true. But it's the cost of the 0th item. Okay, well, what would be the cost of nothing? I mean, theoretically, nothing. But on the other hand, yeah, we could, but also think, if I'm a pizza company and I've sold no pizzas this month, I still have a cost. And that is the cost of the rent and the electricity and the employees and all that stuff. So this thing, even though it is going to be 11 over root 0, and it says undefined, really though, the cost of selling nothing, there could still be a fixed cost. Right? So this doesn't necessarily tell the whole story. If we do C prime of 1, then that certainly is telling us the cost of the first item. But remember, just the cost of the first item doesn't include all the fixed costs. Even here, this doesn't tell us about the fixed costs of the company. Even this one, that's just the cost of the 57th pizza. We still don't know anything about the fixed costs that we have. So does this marginal cost thing tell us anything about the fixed costs? It seems like not yet. We don't understand it well enough to say like, well, yeah, that thing should tell us about fixed costs. We don't know. All we know is that this is the cost of each individual thing, right? But now they're saying find the total cost of the first 49 units. And notice what they're asking us to do. 0 to 49. Well, this is very interesting. I mean, the cost of the first 49 units, I would think that would be the first unit, and then the second unit. But they're having us start at c equals 0, or x equals 0. So what does that imply that this is going to help us find? Maybe it's going to help us find the fixed costs. Maybe the knowledge of the fixed costs is somehow stored inside this formula somewhere. I'm not sure. But what? Yeah, so it certainly begs the question, though. Maybe all they're wondering is the costs of the individual pieces, and maybe we don't know anything about the fixed cost. We shall find out. So let's think about how we could do this. If I want to know the cost of the first 49 units, what could we do? What could we do? We could say this is the item, and this is the cost. So the first item has a cost of c prime of 1, and the second item has the cost of c prime of 2, and the third item has the cost of c prime of 3, and all the way down to the 49th item, which has a c prime of 49 cost. So if I just added all those together, should that be the answer? What?
Yeah.
Oh, why would I do that? Right, right. We're expecting to do an integral, right? I'm just suggesting we think about this a little bit. If this thing is telling us the cost of each individual item, then theoretically I should just be able to add together the cost of each individual item. So one way we could just write the answer down, just for fun, would be total cost equals c prime of 1 plus c prime of 2 plus dot, 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 all the way up to c prime of 49. Does that seem like that would work? I mean, at least that is the answer to the cost of each individual unit. I still don't know that that thing includes the fixed costs. Or if the question is even asking us for the fixed costs.
This is about the
Yeah, it does just say find the total cost of the first 49 units. But then again, see, it still has that very confusing x equals 0, which would be the 0th unit, which is no units at all. So we have some questions here as we try to understand what this is all about. One thing we could certainly do, and I'm sure all of you are very excited about this promising choice, is that we could actually compute this pretty easily, because that's just 11 over root 1, and that's 11 over root 2, and that's 11 over root 3, right? All the way up to 11 over root 49. Is that what we're looking at? And then I could take out the 11, and so then I just have 1 over root 1 plus 1 over root 2 plus 1 over root 3, and I just add that all the way up to 1 over root 49, and theoretically, there it is. So how long would that take me to type into my calculator?
a while.
A while. A minute? Maybe a minute? So we'd have, oh geez. So because you got to do 1 divided by root 1. That would take a while. Yeah, I think so. Is there a quick way that your calculator would do something like this? Does anyone know, does our calculator have a sigma function? A way to add something up? It does? Or does anyone know if there's just an online calculator that we could look up and say, find the sum of a series of terms? I wonder if there's a way to do that. Oh, I would have to type in calculator, online calculator. Series calculator, series and sum calculator. The calculator will find the sum of, ooh, look at this. Sum of 1 over something. Oh, darn it. What was that written? 3 to the n. Okay, so 1 over root n is what I want. 1 over n to the 1/2. Oops, put that 1/2 in parentheses. And a variable, it's auto n. Start value, 1. End value, 49.
Wasn't it 0?
Well, I'm gonna do this one first. Because if I plug in 0, 1 divided by root 0 is undefined. Theoretically, it won't give me an answer. So calculate. Oh, answer. Oh, now look. Did that give the answer that we wanted? No. Look at that weird. Oh, they simplified each one, didn't they? This looks really weird. I don't believe that. This looks real. Oh, and yeah, that is what we want. But then we need to multiply the. Yeah, that is what we want, isn't it? But why does it look so strange? Why does it look like they don't have all my terms? They must have done some really weird simplifying, huh? Plus, it doesn't go all the way up to 49. This is so dissatisfying. What's that? Well, it looks like it only goes up to 47. But maybe that one of these terms at the end was the constant term. Oh, because look, some of the square roots canceled. Look, the square root of 16 is and then lumped all those terms together into this fractional answer down here. Okay, I have confidence. This is it. This is our answer. We just added together 1 over root n. And so now we need to take that sum and multiply it by 11, right? Because I factored out the 11. So I just found the sum of 1 over root all the way up to that, which was? What am I saying it is? Yeah, 12.61. So 11 times 12.61095. Can someone multiply that times 11 and see what we get? Times 11? 138 what?
0.720.
Okay. Okay, well, folks, did we do it? We don't know. Now, just for fun, what happens if I put 0 into my online calculator? Do we think that we should start at 0? Let's see what they do. If I put the start value of 0, are they going to come back and say it's undefined? I was thinking. I'm still thinking, look, I might have tricked it. Oh, the series is divergent. Yeah, so it wasn't able to handle division by 0. It thought that dividing by 0 was infinity, and so they said the sum was infinity. Okay, so definitely can't. Okay, well, at the very least, folks, at this point, would you say that we've approached the problem in a conceptual way, and that we at least now have the exact answer for the individual cost of all individual 49 items, but we have no idea what the cost of the 0th item, which apparently they want us to do. Right? Okay, so now all that said, what should we do next? You probably let's do the integral. Right? We were approaching that from kind of a conceptual approach, but now let's see what happens if we just do the integral. So remember, that's the cost function, the marginal cost function. We want the total cost. So remember, if c prime of x is the cost of one item, what do we want? We want the cost function itself. And then for the cost function itself, we want the cost of all 49 items. What we really want is just c of 49. That's our goal, right? Because if we can just find the cost function and plug 49 into it, that should be the cost of the first 49 items. Okay, so then how do we go from c prime to c? Yeah, that is what the antiderivative is. That's what the integral is. So we're going to take the integral of c prime of x, and we're going to go from 0 to 49 dx. That's what we'd like to do. So hopefully you're all convinced. And why are we going from 0? Well, that's true. It tells us to do it from 0. But also, theoretically, that's going to get at the fixed cost, potentially. We'll find out. So we're going to do this integral from 0 to 49. Okay, so let's try it. So this is really the integral from 0 to 49 of 11 over root x. Let's fix that. 11 over root x is 11 over x to the 1/2, which is really then the integral from 0 to 49 of 11x to the negative 1/2. So does everyone have that? It's really the integral of 11x to the negative 1/2. Okay, so now we did the anti-power rule. So anti-power rule, I add 1, which is really adding 2 halves. So that's x to the 1/2. Divide by what you get. So that's 11 divided by 1/2. And then we're going to evaluate from 0 to 49. 11 divided by a half is just 22. You can do scratch work or type it into your calculator. Make sure you use parentheses around 1/2. So 11 divided by a half is 22. X to the 1/2 is really the square root. And we're going to evaluate from 0 to 49. So now, the fundamental theorem of calculus, look again at how exciting it is that that first number was 0. Now this should be mind-blowing. The 0 didn't even end up mattering. Because when we plug it in, it's equal to 0. Oh my goodness. So that's 22 root 49 minus 22 root 0. Now why would it have been a problem had we put a 1 there? If we had put a 1 there, we would actually have subtracted something. And then that wouldn't have been the full cost. Okay, so then what is that? 22 times 7, which is 140 plus 14, 154. Henry. Sorry, did I calculate that right or wrong? That's right. 140 plus 14? Yeah. What were we saying? Because that's 11 divided by a half. Yeah, so you can do scratch work for that or type it in your calculator. Right?
So if we were to do a indefinite integral, there could be a c which would be fixed cost.
Correct. Absolutely. So if we did the indefinite integral, which would be 11x to the negative 1/2, then that is going to tell us our cost function, because this is c prime of x, so as soon as we take the integral, that would be 22 root x. That is our cost function, but there's a plus c. So now c of x is actually 22 root x plus c. And that c represents our fixed costs.
That's what's matter right now. Or it should matter, but it doesn't.
I don't know that that's the answer. Yeah, we're still figuring things out. But for sure, did this information tell us anything about the fixed costs? No, we still don't know anything about the fixed costs because our answer came out to 138. Their answer is 154. We're still wondering why is that different, right? Why is that a different answer?
All the way
Hmm?
0.1 all the way up to 1 is the difference between 154 and 138.
Could be the difference. What folks do you think is why our answer of the actual marginal cost versus the real answer?
Well, since the derivative is an approximation, then integral is also an approximation of what is trying to represent.
Really close. Remember, when we talk about marginal cost, the derivative is the approximation versus cost of 100 minus cost of 99 to get the cost of the 100th is exact. So if we look at the function 22 square root x, notice that we want the area trapped under the curve. Okay, let me make this look good here. Oops. There we go. So we're going from 0 to 49. So we're looking for all that area right there. Can you see that? No, you really can't. Down there? No, you really can't. Make it smaller. Where did we go? Oh, way too small. There. That's the area we're trying to find, right? So now notice what we did in the first effort versus the second effort. In the first effort, we calculated the height of individual rectangles because I was finding the height at integer values. So really what I did in the first one, when we added all those together, it was a left hand. Yeah, that's what we did in the first attempt. By adding all those individual pieces together, we found rectangles under the curve, which means it was each rectangle is under the curve.
Aren't those slopes though?
Huh?
Aren't those slopes? Because it's the C prime.
But this is C of x, and this is, that's the slope of cost, but this is the cost of that item.
Yeah, but then we added up each cost, which is the C prime. We just added up a bunch of slopes.
They are slopes, but they represent the cost of individual items. Let me finish what I was saying. I see what you're saying. But the answer we got here was an underestimate.
And do you see why it was an underestimate? Because each rectangle is below the actual curve. Whereas, oh, I should draw that straight across so you can see. So yeah, when we first added all that together, it's an underestimate because my rectangles are falling under the curve, whereas this one was finding all the area under the curve. All the area going all the way down to 0. So anyway, I realize class is over. I think I might have held you a minute. Don't worry, I won't charge you for that minute. Okay, so folks, we're definitely done with the problem. The answer is to do the integral. So next week on Tuesday when you come in, you'll all take a test. Feel free to email me over the weekend as much as you like to ask questions. Your practice test, well, let's see, it only has 21 questions on it. And look at the very end of the practice test. It has that flow rate problem. It has that quotient problem. It just has some standard integrals, natural log, that fancy one. All of these are problems that we've done within the last couple days. So theoretically, it's fresh in your mind, and I posted all the solutions online. So please email me with your questions. Monday, if you want to come by Monday, I have office hours from 10:30 to 12:30. So Monday, 10:30 to 12:30, come see me. Or Tuesday, I have office hours from 10 to 11, right before class. So there you have it. You have a chance to see me Monday, you have a chance to see me Tuesday, and you can email me all weekend long. Yeah. 11 divided. Oh, when you added that? Oh, there it is. 11 divided by half. What's 11 divided by half? Just graph it. Yeah, you too. See now. 11 divided by 1/2. Very important if you feel comfortable doing this. That's really 11 divided by 1/2. Which 11 is a fraction, 11 over 1. And how do you divide by a fraction? Yeah, you multiply by the reciprocal. And then straight across, that's 22 over 1, which is 22.
I was like around there, but
Very good. Josh, I can't believe you're going to skip class just because of the lazy American. And now, how did you call that again? A lot of words.